Welcome to the video lecture series EE-371 Electromagnetic Field Theory. The course would be partially conducted by Dr. Husnul Maab, myself, and Dr. Arbab Abdurrahim from Faculty of Electrical Engineering. The tentative semester plan would be 3 recorded lectures per week of 30 to 50 minutes each. Each lecture will have a short assignment which will be graded. Assignment will be submitted via the GIK CMS campus management system. Attendance will be inferred from assignment submission, which would reflect that you have already watched the video lecture. Student can send your question and comments through email or through WhatsApp group or MS Team. Questions needing further explanation in addition to chat will be addressed in the next video lecture. Live interactive sessions may be arranged every 2 weeks to facilitate students if required. A live session will also be recorded and will be available for those who are unable to attend the session. The course learning outcome are as follows. For your information, the CLO1 had already been covered before the midterm. And we have also somehow covered the CLO2. Let me to explain what is CLO1, CLO2, CLO3 and CLO4. CLO1 be able to apply the basic principle of electrostatic theory to electrostatic field problems in various coordinate systems, that is rectangular coordinate system, spherical coordinate system and cylindrical coordinate system. CLO2 be able to analyze electrostatic boundary value problem with associated boundary conditions. CLO3 be able to analyze magnetostatic field problems. CLO4 be able to explain the behavior of time varying electromagnetic fields using laws of electromagnetics. The course contents. We have covered some part of the course contents before the midterm, that is introduction and review of vectors and coordinate system, where coordinate system include rectangular coordinate system, spherical coordinate system and cylindrical coordinate system. We have also covered Coulomb's law, how to apply Coulomb's law to different charge distribution, and electric field intensity. The Gauss's law, how to apply the Gauss's law to different charge distribution. Gauss's law in integral form can be applied to a very highly symmetrical charge distribution, but for asymmetrical charge distribution, then we use the differential form of Gauss's law. Using the concept of divergence, we have defined the Maxwell's first equation. Then we have discussed the energy and potential using the concept of work done in electromagnetic field theory. And in the coming part of the course for online, we will cover these topics: potential gradient, electric dipole and energy density, current and conductor, dielectric and capacitance, Poisson's and Laplace equations, Ampere circuital law, Carl and Stokes theorems, Faraday's laws, time varying fields, Maxwell equations. Let us start the lecture number 26. The topic of this lecture is electric dipole. In this lecture you will learn that what is electric dipole and how to determine the electrostatic field and potential function due to electric dipole at a distant point.
In last lecture we learned that how to convert the line integration of electric field, that is potential relation, into a differential form. For that purpose we use the concept of gradient of scalar potential. The gradient of scalar potential, or simply the gradient, is defined as to give us the scalar quantity, which we can easily convert it into a vector quantity. But the gradient basically tells us about the maximum variation in that scalar quantity with respect to the space and some specific direction. Using that concept, we convert this line integration relation of potential to a very important relation of a negative gradient of scalar potential, which in return give us electric field. In today's lecture you will learn that how to determine or measure, calculate the field due to a dipole. But before going into detailed discussion, I would like to explain that what is electric dipole. So let us consider an electronic atom which is surrounded a nucleus. The electronic atom consists of nucleus and a single electron. The nucleus surrounded by a single electron. By applying the electric field, or keeping this atom in electric field, so there produce a shift between negative and positive charge, and they are not completely isolated from each other. They produce a small shift. This effect is known as dipole moment and is given by this relation P equal to charge on any particle, either a nucleus or an electron, times the smallest distance. This is dipole, electric dipole. That is, in the presence of electric field, there produce a shift in positive negative charge. The magnitude of the charges are the same, but having opposite sign and separated by small distance. So the electric dipole is the electric dipole provide the basis of dielectric material in the presence of electric field, and this also justify the MH theory. Electric dipole is also the fundamental part of any radiating structure. So now the question is how to calculate the electric field and potential due to an electric dipole. Let me to explain that. Now we have a tool, that is how to determine potential electric field from the potential. So let us consider a dipole that is aligned along, suppose along z axis. Suppose positive charge exists above the Z is in Z is greater than 0 region. Let us call it Q1, and this is located at 0, 0, 1 by 2D, and the negative charge is located below Z is equal to 0 Z is equal to 0 plane, that is in Z is less than 0 region. Suppose this is Q2, and this is located at 0, 0, minus 1 upon 2D location. That is, the separation between the two charges is D, and we are actually interested to define the electric field and potential at a distant point P. Let us consider this P point at R equal to R, theta and phi equal to 90 degree. This P point is located from the midway between the two charges at a distance r, small r, or the distance between the midway between the charge and the P point is r, and the distance between the Q1 charge and P point is r1. Let us r1 locate P point from Q1, and r2 locate P point from Q2 charge. Okay, so we are actually interested in electric field and potential field or potential function at P point due to this electric dipole. But remember that the d distance must be much smaller than r. This is the main assumption. This distant point, at a distance point, this is actually our distant point. This distant point, at this distant point, the three vectors are looking the same. They have same value. But when we move very close to the electric dipole, so then we see there is a difference between distance r1 and r, small r, and r2 and r. So let me to explain that what is the difference between the capital R1 and R and capital R2 and small r. We can solve this problem through two different ways. One way to calculate the electric field first at P point, and then using the this relation integration and calculate or determine the potential. But in this case, we have to evaluate this line integration. In order to avoid the evaluation of integration, it will be good to first determine the potential at P point, and then using the negative gradient of scalar potential V, we can easily obtain the electric field. So let us see the step-by-step derivation of potential due to the electric dipole, which is aligned along z-axis at a distant point P. As I told you that there is a difference when we are very close to the electric dipole, so then there is a difference between r1 vector, which is the distance, represent a spacing or distance between Q1 point and P, distant point, and R represent the displacement or distance between the z equal to 0 plane, which is at 0 potential, midway between the two charges, and the field point P. And R2 is the distance between Q2 charge and P point are the field point. When we are very close to the electric dipole, so there is a small difference between the two vectors, that is R1 and R2. So using the geometry, we can obtain the difference between R1 and R2. Let us consider the triangle OAB, and we know that the location of Q1 is located at a distance 1 by 2 d from z equal to 0 plane. Similarly, Q1 is located at 1 by from z equal to 0 plane, or the distance between z equal to 0 plane and Q2 location, which is Q2 is located at 0, 0 minus 1 upon 2d. So the distance between z equal to 0 plane and at z equal to minus 1 upon 2d is 1 upon 2d. So in order to define the difference between R1 and R1 vector and small r, let us consider the triangle OAB. So one can obtain that R minus R1 equal to 1 upon 2d cosine theta. Similarly, consider the triangle OB prime and A prime. So using this triangle OB prime A prime, you can easily define the difference between R and R2 and small r, which is 1 upon 2d cosine theta. And remember that the magnitude of the two charges are the same, but they are opposite in sign. That is the main difference. And the separation between the two charges is very, very small as compared to the distance of P point from the z equal to 0 plane. So it will be very easy to first define the potential. So let us first we know that what is the potential due to a point charge. So we know that the potential due to a single point charge is given by this relation, that is V1 is equal to Q1 divided by 4 pi epsilon naught R1. And similarly, the potential at P point is V2, which is equal to minus Q2, or because Q2 having negative sign or but equal in magnitude to that of Q1. So potential with respect to z equal to 0 plane at P point due to Q2 charge is given by minus Q2 divided by 4 pi epsilon naught R2. We know that the potential is inversely proportional to the single power of the distance between the source and the field point, and directly proportional to the source. So according to Coulomb's law, actually Coulomb's law is linear, so we can easily add the two potential due to Q1 and Q2 at P point using this relation, that is V potential at R position, theta position, and phi equal to 90 degree equal to V1 plus V2. Inserting the relation of V1 and V2 in this relation, we can easily obtain this relation. That is Q divided by 4 pi epsilon naught into 1 upon R1 minus 1 upon R2. Taking the LCM of this relation, So one can obtain this relation. That is one can obtain the equation number 1. Now, how to calculate the difference between R2 and R1 and the product between R1 and R2. So before this, I told you that how to obtain the difference between R1 and small r and small r and R2. So going back to the figure, look at the figure. So from the figure you can get that what is the difference between small r and R1, which is equal to 1 upon 2d cosine theta, and R2 minus r small r equal to 1 upon 2d cosine theta. Using these two relations, we can write the R1, the magnitude of R1 and R2 in terms of the spherical coordinate variable small r and theta. D is represent the separation between the two charges, positive and negative charges. So to simplify or to define the approximate solution of equation number 1, let us first define the difference between the capital R2 minus R1. So using these two relations, so by inserting the value of the expression of R2 and R1 in this relation, we finally come across this relation, that is R2 minus R1 equal to d cosine theta. Now let us define the product of capital R1 and R2. So using these two relations again, and define the product of these two relations. So this becomes equal to r square plus 1 upon 2 r times d times cosine theta minus 1 upon 2 r d cosine theta, and the product of these two terms, this one with that one, becomes equal to 1 upon 4 d square cosine square theta. So look at the sign of this term and this term are opposite to each other. That is, this term is exactly similar to this one, but having negative sign, so we can easily cancel out this term with this one, and we know that that r is much greater than d, so we can easily ignore this, the last term, this one, we can ignore this one, ignore this term. So we left the approximate solution of r1 times r2, which is equal to approximately equal to r square, using this approximation. That is the distance, the distant point, and the distance between the electric dipole and distant point is much greater than the separation between the two charges. So plugging the value of R1 minus R2 in equation number 1, which we have defined using these two relations. So R2 minus R1 equal to d cosine theta, and R1 minus R1 into R2 equal to R square. So replacing R2 minus R1 and R1 times R2 in equation number 1, we obtain this relation, which is written in blue color and is equal to, now the potential is equal to Q divided by 4 pi epsilon naught d cosine theta divided by r square. So if you look at this expression, so we can see that the potential due to 2-point charge is inversely proportional to the square of the distance between the source point and the observation point or the field point. Again, if you look at this relation, so potential is directly proportional to the source charge. Now this equation or this expression is in spherical coordinate system. Now, knowing the potential, now we can easily obtain the expression for the electric field due to electric dipole, but the symmetry of the problem revealed that the resultant field is not a function of phi coordinate. For example, let us again consider the electric dipole Q1 and Q2. So we know that the positive charge produce electric lines of forces in radial direction, in all direction, for example in this. Similarly, all the electric lines of forces are converges to negative charge in radial direction, like this. The symmetry of the problem represents that there exists no phi component because there exists no variation of fluxes in phi direction. So the required field is not a function of phi coordinate. But the resultant field is a function of theta, the spherical coordinate, and the radial distance of spherical coordinate system. So using the negative gradient of scalar potential, expand this relation in spherical coordinate system, which is equal to minus partial by partial r VAR unit vector plus 1 upon r partial by partial phi VA theta plus 1 upon r sin theta partial by partial phi VA phi unit vector. As I told you that the resultant electric field due to electric dipole is not a function of the phi coordinate. Hence, the variation with respect to phi of the potential is equal to 0. So the last term become vanish, and we left only two components of the electric field, which is along the radial coordinate, spherical coordinate axis, and the theta axis of the spherical coordinate system. Differentiate the resultant potential which we have obtained from at a p point due to electric dipole with respect to r and with respect to theta. We come across this solution, and after simplification, the final expression may be written in this form, that is E equal to QD 4 pi epsilon naught r cube 2 times cosine theta AR plus sine theta A theta. The unit of electric field is volt per meter. Remember. The plot of electric field and the potential function of an electric dipole is given in figure 4.9 on page 99 of the book. So I wish that you should reproduce this plot using Mathematica syntax, using Mathematica commands. That is, I would like that you should reproduce figure 4.9 on page 99. Note this one, figure 4.9 on page 99, using stream slice command, stream slice command and quiver. I think this is quiver. Using and plot the figure which is given in the book on page 99. I'm going to show you this one. You should reproduce this figure in MATLAB and submit this by next week, probably on a Wednesday. This one. So now, now we are going to write down the resultant electric potential due to electric dipole in vector form. How to write the potential function due to electric dipole in vector form. So in term of let us write the potential function in term of dipole moment, and hence to represent that potential function in term of vector form, in vector form. So we know that what is the dipole moment, that is q times d. The unit of dipole moment is Coulomb meter. For example, the dipole moment is located by r prime vector from the origin, and the field point is located by r unprime variable. So the resultant vector between the source and the field point is equal, that is capital R equal to r minus r prime. We know that what is QD, and in our case the electric dipole is aligned along z axis, so that means that d distance is directed along z axis. So v at any radial axis and theta direction can be written in a term of dipole moment. So V are equal to P dot AR divided by 4 pi epsilon naught R square. Or in generalized form, you can also write the above expression in this form, which is V as a function of R, and is equal to 1 upon 4 pi epsilon naught R minus R prime whole square. P is the dipole moment dot the unit vector, which is in this case equal to r minus r prime, r minus r prime. Or you can write the said equation in more general form in this way. That is, for example, this is the dipole, and this one is the field point, that is r, and this one is r prime. So then you can also write the generalized form of the potential due to this electric dipole. So then V as a function of R is position vector, this represents the radial distance in a spherical coordinate system is equal to P. P may be in rectangular coordinate system, cylindrical coordinate system, or it may be in spherical coordinate system. Let us consider A is any generalized unit vector divided by 4 pi epsilon naught r square. Or you can use any other symbol for small r. So you can also write down the potential due to the gradient of scalar potential in this form, this generalized form. Let us solve some drill problem, which is D 4.9 on page 100 in the book. In this problem, we have given the dipole moment at a origin in Cartesian coordinate system in nano Coulomb meters unit. The dipole is aligned in free space and at origin, The permittivity of free space is given by 8.854 into 10 power minus 12 farad per meter. We have asked to find the potential at PA point, and the coordinates of P points are 2, 3, and 4. We have also asked to find the value of potential at R equal to 2.5, theta equal to 30 degree, and P equal to 40. And now look at using the foregoing relation that we have obtained using an electric dipole which was aligned along z-axis. So in generalized form, we can write the potential due to electric dipole in this form, that is P dot R divided by 4 pi epsilon naught R square. Actually, in this case, the electric dipole is located at the origin, so that's why the R prime in this case is 0. R prime vector is equal to that has 0, 0, 0 components along each axis. Let us first obtain the R vector where we want to calculate the potential due to the electric dipole, whose dipole moment is given by this vector form. The electric dipole has 3 components along each axis: 3ax minus 2ay unit vector plus az unit vector and nanocoulomb per meter. And also obtain the magnitude from the above vector, R small vector, so this becomes equal to square root 29. Plug in all these information in this relation, and after some mathematical manipulation, we obtain the value of potential, which is equal to 0.323 volt, which is perfectly matched with the answer given at the end of this problem on page 100. Now we have asked for the same dipole moment, we have asked to find the potential at R equal to 2.5, but the point is now given in spherical coordinate system. So we know that the dipole is actually in a rectangular coordinate system. So we first must convert the given point into rectangular coordinate variable. So for that purpose, we use these relations. The relationship between the rectangular variable and a spherical variable is given by these relations. That is, x equal to r sine theta cosine phi, y equal to r sine theta sine phi, and z equal to r cosine theta. Using these relations, we can easily obtain and providing the coordinate of P point, which are in a spherical coordinate system, that is R equal to 2.5, theta equal to 30 degree, and phi equal to 40 degree. So using calculator, we obtain the value of x, which is equal to 0.9576 meter. Similarly, y equal to, for the set points, which is in which R is equal to 2.5, theta equal to 30, and phi equal to 40 degree, which is equal to 0.8035. Using calculator, we obtain the value of z in a rectangular coordinate system for the spherical coordinate variable, that is r equal to 2.5 and theta equal to 30. So this becomes equal to 2.17. In this case, now the field point located by r vector, so the component of r vector becomes equal to 0.9576 x unit vector plus 0.8035 ay plus ay unit vector plus 2.178 theta unit vector. Then define the magnitude of using this relation. Define the magnitude of r vector, which is equal to 2.5. Plug in all these information in foregoing relation. In this one, that is the potential at r equal to 2.5, theta equal to 30 degree, and phi equal to 40 degree, equal to P represent the dipole moment of an electric dipole which is located at origin dot r divided by 4 pi epsilon naught r cube. Using this relation and plug in the values of dipole moment and r vector and epsilon naught, which is 8.854 into 10 power minus 12. The magnitude of r, small r, which is 2.5. So after simplification, we get 1.97 volt, which is exactly similar to the answer given in the book. Now let us apply the same expression or formulas which we have obtained for electric dipole that was aligned along z-axis. Let us solve another drill problem. This D4.10 on page 100. In this case, again, we have given the dipole moment at the origin, and this problem, the dipole moment has only one component, z component, and it again in nanocoulomb per nanocoulomb meter. We have asked to find the potential in first part. We have asked to find the potential at r equal to 4, theta equal to 20, and phi equal to 0 degree. Now, if you look at the dipole moment, so the dipole moment is in rectangular coordinate system, but the field point is given in a spherical coordinate system. We must convert these spherical variable into rectangular variables. So x equal to 4 times using the relation between the rectangular coordinate and spherical coordinate, which to convert the spherical coordinate to rectangular coordinate, we for x-axis we use x equal to r times sine theta cosine phi. For y-axis we use y equal to r times sine theta sine phi, and for z variable or z coordinate, z-axis we use r times cosine theta. So plug in r equal to 4, theta equal to 20, and phi equal to 0. In this relation, we can easily define the values of x, which is equal to 1.368, y equal to 0, and z equal to 3.759. Now we can easily define the vector that locate the field point, that is P point, in rectangular coordinates. In a rectangular coordinate system, that is r equal to 1.368 x unit vector plus 3.759 az unit vector. Again define the magnitude of r, which is equal to 4.002. So now again use the potential expression which we have, the generalized potential expression which we have obtained for the electric dipole. Plug in all the information, that is the dipole moment, the vector that represent the position of field point from the source, and using the free space permittivity, because the electric dipole is aligned in free space. So by inserting all these values in the expression for potential due to an electric dipole. So we, after simplification, we got 3.16 volt, which is exactly matched with the answer given in the book. Now we have asked for the same point. We have asked to in part B of the drill problem D 4.10 on page 100, we have asked to find the electric field due to electric dipole aligned along z-axis. So for electric dipole, we have obtained the electric field using the negative gradient of scalar potential. Using that relation and plug in all those, plug in the value of r, theta, p, the component. Actually, in this case, now we are taking the component of p, or the magnitude of p, which is 6 into 10 power minus 9. Plug in all these the numerical values of theta and r, so eventually we come across this expression, that is E equal to 1.858 AR plus 0.288 A theta. Actually, in this case, the electric dipole is aligned along z-axis, so that's why the electric field has two components, one along radial axis and other along theta direction. Now I would like that you should obtain the electric field for the electric dipole at origin, which is the dipole moment of D4.9. I wish that you should obtain the expression for electric field for these points for part A and B, and submit that problem in on Wednesday in next week. And that is, you should obtain the electric field for given dipole moment. This is an assignment for you people, using the information given in drill problem D4.9 on page 100, and submit the soft copy of this assignment on coming Wednesday next week. I have also assigned you the plot of electric and magnetic, the electric field and potential due to electric dipole. You should also reproduce that plot and submit that by next week, till by Friday. This is let's consider this our first problem, and this is our first assignment, second assignment. Submit this assignment by next week on Friday. Please provide soft copy of these two assignments. Thank you.